So this is the review video for bijections and Fermat's little theorem. So let's get started. So first, a bijection has to have two properties. It has to be both surjective as well as injective. And so if we had some function that mapped inputs A to another set of inputs B, in other words, the domain is the set of elements in A and the range is the set of elements in B, then for it to be surjective or onto, it just means that every possible element in the set that is the range, or every element in B, it has to have an element in the domain or in the input that maps to it. And basically all this means is just that every single element in the range is mapped to. So for example, if we had f of x equals x plus 2 mod 5, it is surjective because, first of all, in the world of mod 5, the range could only take on values 0, 1, 2, 3, or 4, and we'll notice that there does exist a value x that makes sure that every single value in the range, 0 through 4, is indeed mapped to, and that happens to be 3 for 0, 4 for 1, 0 for 2, and etc. You can read the rest. And now we'll look at a function that is not surjective, and that's f of x equals 2x in mod 4. So you'll notice that out of all the possible values in the range, which in the world of mod 4 would be 0, 1, 2, and 3, not all of these values, specifically 1 and 3, are actually mapped to, or actually able to be obtained given f of x. Specifically, you can only get the values 0 and 2 in the range, no matter which value of x you give. So thus, since there are some values in the range of f of x equals 2x mod 4 that cannot be mapped to, then f of x equals 2x mod 4 is not actually surjective. So now we'll look at what injective is, and that's very similar to what we learned before in like calculus in high school, and that just means a function is one-to-one. So that just means that every single element in A also outputs a distinct element in B, or really that whenever you give any specific number x, whenever you give any specific value for x, it'll also give you a distinct value f of x or a distinct value of y. And what this implies is that if you had two elements that gave the same value f of x, then that means that x has to be the same exact number. And that'll make a little more sense when we see examples. For example, good old f of x equals x, specifically in mod 5. That means that the domain can be 0, 1, 2, 3, or 4, and then the possible values are also 0, 1, 2, 3, and 4 for f of x. And it's pretty obvious that when the only way that you can get 0 given f of x equals x is by inputting 0, the only way to get 1 is by inputting 1. And so every single value in the domain, 0 through 4, also gives a unique value 0 through 4. So again, the only way that you can get 0 is by inputting 0, getting 1 by inputting 1, etc., etc. And then now we'll see that actually the same function from the last slide is also not injective or one-to-one as well. And we can see this because you'll find that multiple values of x, or multiple values in your domain, can actually map to the same exact value in your range. So, for example, for the value in the range that is 2, you can actually obtain 2 by inputting either 1 or by inputting 3. And the same goes for if you want to get 0, you can actually have two different numbers in the domain, specifically 0 or 2, that will give you the number 0 if you plug them into f of x equals 2x mod 4. So that is injective, and basically a bijection just means that it's both surjective and injective. And so now we're going to see an example a little more visually what this means. A more layman's terms of saying what a bijection is that simply that every single value gets mapped, every single value in the domain actually gets mapped to another distinct value in the range. So since every single value in the range gets mapped to, and since the function is one-to-one, it just means that every single value in the domain maps to a specific, distinct, unique value in the range. So for example, if we had f of x equals 2x mod 5, if you were paying attention to the previous slides, you'll notice that it's both surjective and injective. And visually, all that really looks like is that 0 will map to 0, 1 to 2, 2 to 4, 3 to 1, 4 to 3. And what that looks like visually is that every single input, or every single value in the domain, actually maps to a specific unique value in the range. So again, 0, 0, 1, 2, etc., etc. And so now we'll actually use this idea of a bijection to actually prove Fermat's Little theorem. Now specifically, Fermat's Little theorem states that for any prime p and any a in the set 1 to all the way to p minus 1, it states that a raised to the p minus 1 power is equivalent to 1 in the world of mod p. So for example, if we had Fermat's Little theorem and we were working in the world of mod 5, then 1 to the 4th, 2 to the 4th, 3 to the 4th, 4 to the 4th, and 0 to the 4th. Oh, that's actually an error. 0 to the 4th is actually 0, not 1. So just 1 to the 4th, 2 to the 4th, 3 to the 4th, and 4 to the 4th are all equivalent to 1. Now we're going to move on to the proof. So the first thing that we're going to do is prove that a certain specific function is actually a bijection. We're actually going to use the function f of x equals ax in the world of mod p. And this was a question that was asked in the lecture, like why specifically do we choose f of x equals ax mod p? And we really actually only choose it because it's very easy to manipulate to get into the actual claim or the actual conclusion of Fermat's Little theorem. So we're going to prove that f of x equals ax mod p is actually a bijection. And first we're going to prove that it's injective or one-to-one. We're just going to do this with a really quick proof by contradiction. So suppose that there are different numbers, x and x prime, so like maybe 1 and maybe 2, and it actually is possible that ax is the same value as ax prime in the world of mod p. Now, since we're in the world of mod p, and p is prime, then a also has to have a multiplicative inverse, and that means that we can multiply both sides of that previous equation, ax equals ax prime mod p, by a to the negative 1 on both sides, do some algebra, and we find a contradiction that x equals x prime. But right above we already said that x and x prime are supposed to be distinct. So then by contradiction, there must only be a single value that can map to a single f of x. So if you have two numbers that gave the same value f of x, specifically ax mod p, then they have to be the same exact number x. You can't have two single values for x that will give you the same ax mod p. So now we'll do a little kind of more explanation of why it's surjective. And now the reason why it's surjective, and it's actually enough to simply prove that this function is actually one-to-one, is that we can observe that both the domain and the range of f of x is the numbers 1 to all the way to p minus 1. Which is the same as the possible values for a as given by Fermat's Little theorem. And the reason that the domain and range are these values is because we simply defined the range and domain as the set S, which to go along to make it fit Fermat's Little theorem we simply define as 1 all the way to p minus 1. Now the way that you want to think about this is that since the range and the domain are both all these numbers from 1 to p minus 1, then if a single number in the domain, such as 1, maps to a distinct number in the range, let's say p minus 1, then simply enough, if every single number in the domain matches to another distinct number in the range, and the range is the exact same number as 1 to p minus 1, then it means that every single number in the range has to get mapped to. Because if you have, let's say, 5 numbers, 1 through 5, in the domain, and each of those 5 numbers maps to another distinct number, and you know that every single number in the range is also a number 1 through 5, then it means that if 1 maps to a distinct number, 2 maps to a distinct number, 3 maps to a distinct number, that simply means that every single number 1 through 5 in the range also has to be mapped to. And so, proving that the function f of x equals ax mod p is indeed a bijection, we can move on to possibly the less intuitive part that might be a little more confusing. Now specifically, we're going to try to manipulate f of x equals ax mod p to yield a to the p minus 1 equals 1 mod p, which is the claim by Fermat's Little theorem. Now the first thing that we need to notice is that since f of x is a bijection from s to s, the same numbers 1 all the way to p minus 1, then the elements of the domain and the elements of the range are the same, 1 all the way to p minus 1. And so what that implies is that if we were to multiply all the possible values of x, we'd simply get all the numbers 1 to p minus 1 multiplied together, which is simply p minus 1 factorial. 1 times 2 times 3 times 4 all the way to p minus 1, just p minus 1 factorial. And then if we multiply all the possible values of f of x, we're going to get something kind of similar. Specifically, we'll get a times 1, a times 2, a times p minus 1, etc., etc. And that's just because if we multiply all of the ax's together, and x being 1 to 2 to p minus 1, you simply get a times 1, a times 2, a to the p minus 1, which is simply a to the p minus 1 times p minus 1 factorial. And again, that's simply because 1 times 2 times 3 all the way to the p minus 1 is p minus 1 factorial. And since there are p minus 1 numbers in this range, or in this domain rather, then we simply multiply by a p minus 1 times. So now the key observation is that since all the numbers in the domain of x are the numbers 1 to p minus 1, and they all only appear once, and then for the range, or the values of f of x, it's also the same thing. It's all the numbers from 1 all the way to p minus 1, and each of those numbers also appears only once. So basically, if you're multiplying all the values of the domain, all the values of the range, then you're going to get the same exact number. Now, this is probably the most confusing part of Fermat's little theorem, so we're going to see like a small example and try to see it a little more visually. So let's say that we have the specific scenario in which for f of x equals ax mod 5, we instead have f of x equals 2x mod 5. So in this case, x could be 1, 2, 3, or 4, a equals 2, and our prime number p is 5. So let's multiply all the possible values of x, which are going to be 1, 2, 3, and 4. So obviously 1 times 2 times 3 times 4 in the world of mod 5 is simply 4 factorial. And then now the tricky part is multiplying f of x, all the possible values of f of x. So to do that, we're simply going to plug in all the possible values of x. So since we know that f of x equals 2x, if we were to multiply all the values of f of x, it would simply be 2 times 1, 2 times 2 times 2 times 3, 2 times 4, all in mod 5. And so we're going to simplify that. So 2 times 1, 2 times 2, 2 times 3, 2 times 4 is simply 2 times 4 times 6 times 8 in mod 5, which we can then simplify in mod 5. So that's 2 times 4 times 1 times 3, which turns out is the same as 4 factorial. So what you can see is that if you multiply all of the values of x, or all the values of the domain, then you actually get 4 factorial. And if you were to multiply all the values of the range, or all the values of f of x, you would also get 4 factorial. So what this shows you is that when you multiply all of the values of x, you actually get the same exact thing as if you were to multiply all the values of f of x. And the only difference between x and f of x, when you're multiplying them all together, is that f of x has this constant a whenever you multiply it. So we'll see this a little more formally, but you can think about it that the only difference between multiplying all values of x and multiplying all values of f of x is simply that you're multiplying by a when you multiply by f of x. So since there's p minus 1 values of f of x, you're multiplying by a p minus 1 times, or a to the p minus 1. But let's go ahead and see that a little more formally, or a little more visually, and we'll see that since we're able to equate the product of the domain and the product of the range, we can get this equation. P minus 1 factorial is actually equal to a times p minus 1, a raised to the p minus 1 times p minus 1 factorial mod p. Then we can see that p minus 1 factorial is some number in 1 to p minus 1. We know it's not 0 since none of 1 through p minus 1 is a multiple of p. And since p is prime, then p minus 1 factorial has to turn into one of these numbers, and it has to have a multiplicative inverse. So we can just multiply both sides of this equation by the multiplicative inverse of whatever p minus 1 factorial is, and so we can cancel both sides of this p minus 1 factorial, and we yield our claim that a to the p minus 1 equals 1 mod p. And now, just again, another way to think about it, if you don't want to think about the algebra, is simply that if we know that multiplying all these values of x gives us the same thing as multiplying all the values of f of x, and that the only difference between x and f of x is this constant a, then we can realize that multiplying by a, p to the minus 1 times, since there's p to the minus 1 elements of both the domain and the range, simply has to equal 1. Because if we get the same thing here, when multiplying all f of x as the same as the product of multiplying all the values of x, then clearly a to the p minus 1 has to equal 1. And so those are bijections and Fermat's little theorem, and hopefully that helps, and hopefully that didn't confuse you anymore.